Okay, so moving on from a hypothesis test situation when sigma is known to one where sigma is unknown, this is the more usable test statistic, or the more practical test statistic. Again, sigma is a population parameter. We're typically not going to know it. So this is, in this scenario here, there's two types of test statistics we're going to consider. One is when the sample size is large, that is at least 30, and the other when the sample size is small, we'll say less than 30. Okay, but the data comes from a normal or a near normal population. Okay, scenario one, large sample case. The conditions here are that we have a random sample, a large sample, and sigma is unknown. The test statistic here looks just like the one that we had before, but what we've done is we have replaced sigma with S, and that's a very natural thing to do here. And it turns out that this test statistic has an approximate standard normal. Let's see here. This test statistic is approximately standard normal under the null hypothesis, and this is by the central limit theorem. So the CLT is driving this result here. This test statistic is analogous to this confidence interval. In other words, this confidence interval x bar plus or minus z times s over root n, when we use that interval we had the same conditions as what we have here. Okay. Scenario 2, the small sample case. We have a random sample, any size sample. Here I say small sample, but if it works for small samples, then it will work for large samples here. We don't need any kind of central limit theorem result in order to use this method. Third condition is that we have a normal or near normal population, and that sigma is unknown. Now, the normality assumption can be checked by looking at the histogram or the QQ plot of the data. If the histogram is close to bell-shaped, or if the QQ plot is approximately linear, then normality is tenable. The test statistic here is the same structure, the same ratio as above, but we call it a T. We define it as T because the distribution of this test statistic under these assumptions follows a T distribution. So the distribution of this test statistic here is T, student's T distribution, with degrees of freedom equal to n minus 1, and that's the distribution under H naught. So we sometimes call that the null distribution of our test statistic. This test statistic is analogous to this confidence interval, x bar plus or minus a T percentile times S over root n. Okay, the conditions when we use this confidence interval formula is the same as these conditions here. Okay, so let's look at an example. Take a moment and read this example. Take a look at the output. This is output from JMP. Again, for you to get this output in JMP, you may want to verify it yourself given this data set that's listed here. The JMP demonstrations should give you some insight into how to get this particular kind of output. Okay, so take a moment and read this example. Alright, so a machine that produces ball bearings is set so that the average diameter is 1/2 inch. Alright, now this is an important problem. If you've ever dealt with ball bearings in some sort of typically an automotive or some application or some sort of application where we have something spinning over a shaft. Most popular now are those fidget spinners. They have ball bearings in them, and the ball bearings have to be of a certain size. If they're out of tolerance, then they're not usable. They're not going to do their job as well as they should. And so here's this machine. We want to test, is the average diameter of a ball bearing equal to 1/2 inch, or really not equal to 1/2 inch. That's what we're after here. This is the claim that we want to test. All right, we want to get at that. And so, thinking of this as a hypothesis test, I'm going to go through the steps here. I'm going to define the parameter of interest. That parameter of interest would be mu, and of course that's the mean diameter of all ball bearings made by this machine. Okay, and the null and alternative hypotheses are as follows. Again, I recommend that you identify the alternative hypothesis first. The alternative hypothesis here is that mu is not equal to 1/2 inch, and so that's the claim. We want to test. That's the alternative hypothesis. Do we have enough evidence to go from H0 to H1 with an overwhelming statement and strong confidence? The null then is just that mu is equal to 1/2. Remember, the two hypotheses are competing, so we would have mu is equal to 1/2 for the null hypothesis. And so in the context of this problem, in the manufacturing of these ball bearings, if there was strong evidence to go from here to reject this and accept this, well then what might happen is, or what might be going on is, that might be indicative of the ball bearings, the quality control having some problems, and a lot of ball bearings are being put out there that aren't really close enough to 1/2 inch to be usable in the way they were intended to. And so if this was a process, perhaps at this step, if you rejected the null and accepted the alternative, you would stop that process and go try and fix the machine. Okay, this is a common sort of thing within quality control or just the manufacturing industry. So that's step one here. Now let me come to the analysis a little bit, just to draw some distinctions here. This 4.93, that's not mu, right? That's not mu. That's x bar. That's the mean of the sample. My screen has gone away. That's the mean of the sample. And this 0.022 quantity, that is S, the sample standard deviation. And for what it's worth, here we have the distribution, the quantiles for and certain percentiles for this data set. Here is the box plot. Here is the histogram, and so forth. And so I'll come back to that in a little bit, but let's continue on with the actual hypothesis test. Step two, if we're going to test a population mean, we really have three scenarios to consider, and two of the scenarios, one of them requires a large sample, and we're not in that scenario clearly with just 10 ball bearings. The other scenario the first scenario that we looked at in the previous video, is that sigma is known, and that's clearly not the case here, and in most practical settings that's not the case. So are we in this third scenario? Are we in the scenario where we would use this t distribution? Do we have a random sample? We have a small sample? Do we have a normal or near normal population? Is sigma unknown? Are we in that situation? So what we have here is a random sample, yes, and sigma is unknown. I've got a statement in here that says you may assume that ball bearings are approximately normal, but if we want to go a little bit further, we could actually look at the QQ plot here in JMP, and the QQ plot, given that it's fairly linear, that supports the assumption of normality. Okay, so we're going to go along with that assumption, and hence along with that t test statistic. So here in step 2, when we think of, okay, what's our test statistic and its distribution, we're dealing with the t test statistic. Okay, so the test statistic and its distribution. This t ratio here, x bar minus mu naught over s over root n. That's our test statistic. Its distribution follows a student's t distribution. Follows a t distribution with degrees of freedom equal to n minus 1, which in this case would be 10 minus 1, 9 degrees of freedom. That's step 2. Step 3, the significance level. Alright, here alpha, you can look back up in the problem, alpha was chosen to be 0.01. Remember, alpha is the probability probability of a type 1 error that we're willing to live with. Alright, that's the significance level. The rejection region here, draw a picture of that. Remember, the rejection region just tells you where you're going to reject the null hypothesis, and so the rejection region here is going to be on this t distribution. Here the mean of t is 0. Here is the t-axis here. Now, one thing about this rejection region, it's a little different than what we had before. Before we had a one-sided rejection region. We had a right-tailed rejection region. We would reject H naught in this previous example if z was bigger than 2.33. Okay, remember that was working off of this alternative hypothesis being greater than 43.5. Now, what we have is different in this example here with the ball bearings. Let's see if I need to reduce that. With the ball bearings, we don't have a right tail test, we don't have a left tail test. This is called a two-tailed test. And one reason it's called a two-tailed test is this alpha is split into the two tails of the distribution. Okay, and so we actually split the alpha in this way. We're going to have here t sub 0.01 divided by 2, and over here we're going to have negative t sub 0.01 divided by 2. And if you look that up, that is t sub 0.05. I'm kind of out of space here. This is negative t sub 0.05, and hopefully you've budgeted your space better than me. But if you look these two values up in a t-chart, you should get something that would be 3.25, and that would be negative 3.25, and anything to the right of these values, this 3.25, or to the left of negative 3.25, would be the rejection region. Okay, and it's intuitive. If you look at it, the alternative hypothesis is not equal to, so what we have to do in order to have overwhelming evidence that would go from H naught, that mu is a half, to H1, that mu is not a half, the overwhelming evidence could be in the form of x bar being a lot bigger than mu naught or a lot smaller than mu naught. Well, a lot bigger would be reflected in a large t value greater than that. A lot smaller would be reflected and a t-value less than that. Okay, and so this is somewhat intuitive here. So we have a two-tailed test, a two-tailed. Oh, I think I made a mistake here. You may have already picked up. This is t subscript 0.005, and same thing here, 0.005. Sorry about that. So just to be clear, the area of the curve to the right of that is 0.005. Area under the curve to the left of that is 0.005. Okay. To add on here, if you wanted to think about what does the decision rule look like, it would be to reject H0 if t is bigger than 3.25 or less than negative 3.25. What's typically done is we say if our observed test statistic, if the absolute value of it exceeds 3.25. Absolute value, recall, is it takes anything that's inside of it and makes it positive. Okay, it deals with the magnitude of that quantity and ignores the sign. Alright, so that's step 3. Step 4 here, checking assumptions. We kind of did this in terms of talking through it, but I'll write it out here to be formal. The test statistic, the t-test statistic, the test statistic here, or the test statistic in step 2, is valid because A, we have a random sample, B, sigma is unknown, and C, we have a small, any size sample, so that's not really an assumption we need to check. But the other one that we do need to check is normality was tenable based on the QQ plot. C, normality is tenable. Let's see here. Alright, so assumptions, we're good to go there. Next step, descriptive statistics. Well, from jump, we didn't do this by hand, but from jump, we had x bar was equal to 0.493, s 0.0221, and of course the sample size was 10. Alright, and now let's compute the actual test statistic. So the actual test statistic here, the observed test statistic is again x bar minus mu naught over s over root n. X bar is 0.493. Mu naught, that's the value of mu under the null. The value of mu under the null, here it is, 1/2. Okay, so we're going to plug in 1/2 there. Divided by s, 0.0221, over root n, divided by the square root of 10. And if you do the computation there, you're going to get negative 1.00. Okay, that's our test statistic. Now, looking at the jump output, part of running the test mean and jump, oh, I don't have that in here. You can actually run the hypothesis test within jump. I don't have it on this example. I'm thinking of another one. But it would compute this test statistic for you. Okay, step 5. Step 5 here, let's make a decision and let's interpret it. So we'll make a decision and interpret it. It would look like this. we ask the question, is our observed test statistic in the rejection region? Well, -1 is somewhere over here. So it is clearly not in the rejection region. So we fail to reject the null hypothesis. So let's make that clear here, because t observed, which is -1, is not in the rejection region. We fail to reject H0. Okay, so what does that mean? Well, in the context of the problem, it means we don't have strong evidence to conclude that this is the case. Now, we're not disproving that, but we just don't have strong evidence to support that the average diameter of all ball bearings from this machine is off of 1/2 inch. Okay, and on the same side, that's not, on the same coin, that's not the same as saying that mu is equal to 1/2. We're not saying that either. We're just saying we don't have strong evidence to reject that. Okay, so let me write that out in terms of an interpretive statement. So we would say here, therefore, we do not have sufficient statistical evidence to conclude that the average diameter of all ball bearings, let's see here, ball bearings is not 1/2 inch. Okay, so that is our interpretive statement. Alright, that's a t-test example. A t-test, I didn't really highlight that, but this scenario here, this is called a t-test. Alright, t-test for a single population mean. Okay, here is another example that I want us to look at here. And this is actually from your textbook. It's from Ott and Longenecker, edition 6. And take a moment and read this problem setup. Okay, so here we're doing inference on the average dissolution rate for this particular drug. The data, the sample here, there's 24 sample points, and the summary statistics are given in JMP. The average dissolution rate for the sample was 19.83. The standard deviation there, S, for the sample, S is 0.432. Okay, and one cool thing within JMP, we even automatically get this confidence interval on the population mean. But let me scroll down to to the question to have a little more context. We were testing here the mean dissolution rate is mu. It's a population mean mu. Do we have evidence? Is there significant evidence that this is less than 20, which is 80% of the labeled amount? So just to set up the null and alternative hypotheses here. Now on this example, I'm not going to go through all of the I'm not going to go through all 5 steps of the hypothesis test. I want us to just set up the hypotheses, know what the parameter of interest is, look at the JMP output, and make a decision based on that. And so setting up the hypotheses here, we're asking the question, is there evidence that mu is less than 20? We have evidence that mu is less than 20. And the null then would be that mu is greater than or equal to 20, or if you just had greater than, or I'm sorry, if you just had equal to 20, that would be okay. We're going to use the t-test here. The t-test output from JMP is as follows. You can see it. Here's our t-test value, the observed test statistic. Let me hit the pause button. Well, not literally, but think about, I'm wanting to use a t-test. I got to ask some questions. Are my assumptions satisfied? Alright, let's go back. Look here at the QQ plot. The QQ plot looks, it doesn't quite look as linear as the previous one, but there's not a lot of points. There's not any points that are outside the dashed curves there, which would be a strong departure from normality. And so we're going to continue with this assumption that normality is okay. And we are actually, it turns out the t-test is somewhat robust to departures from normality. And given that we have 24 data points, we're doing pretty good here, because the central limit theorem is also going to help us a little bit. Even though we're not to that 30, we're close to it. So I'm going to go along with the assumptions that the t-test is okay. And in this t-test scenario here, this is our observed test statistic. Now what JMP gives us is it gives us the output for this is a two-tailed, this is a p-value for a two-tailed test, and this here is a p-value for a right-tailed test. This is a p-value for a left-tailed test. And we are in the situation here of a left-tailed test, right? We have that mu is less than 20 in our alternative hypothesis. So with that p-value, it's 0.0325. Is that smaller than the alpha that was specified? So we're going to make our decision. Where's the alpha? The alpha here. Use a significance level of 0.01. So it is, it's not smaller. I'm sorry, it's not smaller. I was thinking. Anyway, it's not smaller. So we would fail to reject the null and accept the alternative here. So, but if the alpha was larger, if it was 0.05 or even 0.10, we would reject the null and accept the alternative. So the setting of alpha to be 0.01 is a reflection of being very careful to guard against a type 1 error. All right, so that's we don't want to erroneously conclude that mu is less than 20 when in fact it's not. The consequence there is higher than it is for a type 2 error. Okay. So what we would do here is we would fail to reject H0 due to the p-value. I'm going to make this 1, 2, due to the p-value being larger the alpha 0.01. By the way, yeah, that being 0.01. So the way we would interpret this is that, again, we do not have sufficient statistical evidence to conclude that the mean dissolution rate is less than 20 milligrams. Okay. That is a t-test, largely using JMP to do the bulk of the work for us. We look at the p-value, make a decision, but you have to know what's going on in the background to fully appreciate the output that JMP gives you here. Alright, that was another t-test and jump. Moving on here, one more page for this video. I know it's been kind of a long video, but this is a good place to, a good thing to tack on the end of this video. Then we'll start our last one after this section. The power of a test. We had talked about this briefly. The power of a test is the probability that the test rejects a false null hypothesis. And so you want this thing to be high. The power of the test is 1 minus beta. Recall, beta is the probability of a type 2 error. Now, what we do here is we attempt to design tests that have large values of power and hence small values for beta, type 2 error rate, Now, what we're going to do in computing the power of a test would be to let mu naught be the null value of mu, that's the null hypothesized value, and let mu a denote the actual value of the mean and the alternative. And so in real life you're not gonna know the actual mean, but we're saying if we did know it, we want to know what our power of the test be. Okay, the formulas that are about to follow will allow us to compute that. We're going to let beta of mu a be the chance of a type 2 error if the actual mean is mu a. And then the power of the test is going to be 1 minus beta. Notice I have beta of mu a as kind of like a function notation. This is saying that the power is a function, or it depends upon the actual value of the mean. Now, I'm not going to derive these formulas here. I'm just going to present them to you. For a one-tail test, a z-tail test in particular, this formula here gives us the type 2 error rate, and 1 minus that would give us the power. And so it's a probability. It involves the critical value, the null hypothesized value, the actual value of the mean, and then sigma y hat, that's going to be sigma over root n. Okay, so that's for a one-tail test here. For a two-tail test, we have a similar sort of formula, but it's actually this is what's different here. The subscript on the z is different. That critical value there is different to accommodate for the two tails, and actually this formula gives approximate values for that power, so be aware of that. And for the t-test, see your text for the t-test. I'm not going to spend a lot of time on it here in this video, but I want you to be aware, mainly what I'm getting at here, I want you to be aware of the power of a hypothesis test. Okay, so we're going to revisit this earlier example where we dealt with the price of a history book, or the average price of history books, and we want to compute the probability of a type 2 error regarding the price of a history book, assuming that mu sub a is 48.5. That is, if we knew the population mean was 48.5, what's the chance of a type 1 error? That's what we're going to compute here. What's the chance that we would draw a sample that would yield a test? I'm sorry, what's the chance of a type 2 error? I misspoke. What's the chance that if we draw a sample that would yield a test that would not reject the null when it should have, if in fact mu was 48.5? So beta of mu a, alright, so this is going to be beta of 48.5. So just using the formula above, this is a one-tailed test if you recall. So this is a probability regarding the standard normal variable z. That's the probability that a z is less than or equal to. The z value there is the critical value there was 2.33, recall that, minus the absolute value of mu naught, which is 43.50, minus mu A 48.5. Okay, take the absolute difference there, divide it by sigma over the square root of n. That's what sigma y bar is. Okay. My computer, you may have not noticed that, but sometimes my computer jumps to a different screen. This touch screen is pretty cool in what it can do, but sometimes it will jump to a different screen when it shouldn't. Alright, so anyway, if we simplify this, if you do the arithmetic over here, do that arithmetic, it may take you a minute, but verify that you get negative 1.83. Okay, so you take your z-chart, look at the area under the curve to the left of negative 1.83, and you get 0.0336. So this says what? If the true value of mu was 48.5 and you were doing that same hypothesis test that we had before, that we were testing as mu bigger than 43.5, the chance of you not rejecting that false null hypothesis for a sample of size 40 is just a little bit over 3%. So pretty small chance of you making a type 1 error. What is the power then? Well, this is pretty straightforward here. Therefore, the power of the test at 48.5 is 1 minus that quantity, which is 0.964. So the power of the test is very high. So let me give you a good interpretive statement here. This says that if, it's a big if, but if the true mean is 48.5, then before a sample is drawn, or a sample of size 40 is drawn, we have a 96.4% chance of correctly rejecting the false null hypothesis. Okay, that's what that says there. So, power of the test. What I would want you to be aware of is if you look at this figure 5.14, it gives you some insight into the relationship between the power of the test and the sample size and significance level. I say power, type 2 error rate. Just to make a statement here, then we'll be done. If mu A is closer to 43.5, the closer the true value of mu is to the null hypothesized value, then the type 1 error is going to go up and the power would go down. Okay, and you could verify that if you put in a smaller value here, then you're going to subtract off a smaller amount from 2.33, and that's going to in turn make this quantity maybe potentially still negative, but not as far to the left, and in turn this probability won't be as small. Okay, that concludes this video.